today we're going to hear a talk of Professor Emili Bifet. He is going to talk about Tamagawa numbers and characteristic classes, right?
Mm-hmm. Thank you. Well, let me begin by saying that it's nice to be here. It's very nice also to say hi to Han, who may be watching this afterwards. I hope he comes back soon. So today's title is Tamagawa numbers and characteristic classes. I find it's a tough talk to give because there are lots of things coming in. But I hope that at least at the end of it, you may feel that you have a feeling for what Tamagawa numbers are and why we care about them. So let me write the title first. So Tamagawa numbers and characteristic classes. And what I'm going to try to do today is to explore some transition functions within these two charts. Let me begin with Tamagawa numbers. And I'm going to begin with Lagrange. It's quite well known that if you consider an integer n, and you look at the equation given by adding 4 squares and setting them equal to n, well, it's well known that these can be solved in integers. What's not so well known, although it's a very classical result, is that you can give actually a quantitative answer to in how many ways this can be done. And in fact, this was done by Jacobi in the Fundamenta Nova, this classical work. And the answer comes simply to be in, I think it's 8 times the sum of all the divisors of n and the sum over those numbers is a 4d divides n. And of course, the way this is done is by looking at the generating function for this number. That's just the 4th power of some value of some theta function, and you can equate that to another function and you get these wonderful results. So here we have a qualitative question. Here we are giving this quantitative answer. Of course, this is more precise, actually implies this one. So let's go on, and let's generalize all this problem to a very broad setting of quadratic forms. And let's consider the equation now, x t s x equal to t, where now s and t are symmetric matrices, and so you should think of this s and t as being quadratic forms if you wish. And we are considering this equation. Of course, this is in a set of mathematics that goes back to Gauss, when the discretizations started by considering binary quadratic forms. Let me quote here a qualitative result by Hasse that says essentially that you can solve these over the rational numbers if and only if you can solve it over the integers modulo any n and over the real number. Usually this is rephrased in terms of p-adic numbers, but it's the same thing. This is certainly a qualitative statement that extends the previous one, but it's a much broader statement. And let me go into the quantitative side of things. And here we get the work of Ziegel. Ziegel, of course, was building on previous work by Gauss, Dirichlet, Eisenstein, Henry Smith, who is not so well known these days, but was fairly well known during the last century, and Minkowski. And he sort of gave the final formula. And that's what I would like to talk about in this preliminary part. So let's assume for simplicity that S and T are positive definite. And let's look at the number of solutions in integer matrices X to this equation. Let's call that AST. Let's equal that. So that's the number of solutions in integers. And let's write also A sub Q of ST for the number of solutions modulo Q, where Q now is any integer. The statement we would like to have somehow is a statement that would relate these two numbers. But of course things are not so simple, because if you have a solution in integers here, then suddenly you get a solution over the real and over all the integers mod any number. But of course the converse is not true. What I mean is that if you have two forms that are equivalent over the rational numbers, then they will be equivalent over here. No, I'm saying it wrong. If a form represents a number in here, it's going to represent them. Let me back up. Let's define an equivalence of forms. And we'll say that two forms are equivalent if they represent each other. That is, I can exchange them in here. What's going to happen now is that I'm going to have some equivalence classes for that relationship. But I have to jump to a higher situation, which is the genus, because I have to worry about what happens over here. I may have situations where I have equivalents. If they're equivalents over the integers, they're going to be equivalent here. Forget the rationals. That's getting me wrong. But if they're equivalent here and here, they will be equivalent over the rationals, but they may not be equivalent over the integers. So that introduces for us the need to divide the forms not only into classes, but into this higher thing called the genus. So a genus is going to divide up into different classes. But for our situation of positive definite, this is going to be just to find a number. Let's say H, and that's the class number. So we may assume that we have some representatives given the genus of S for the different classes. Let's call them S1 to SH. So Siegel's idea now, and this is in a way going back to Eisenstein, is to consider some sort of mean of the number of solutions over the different classes in the genus. And so let's define this mean number to be sum over the different classes in the genus of A SIT over A SI. And all of these divided by what Einstein would call the weight of the genus, which is sum, again, over the same integers of 1 over A SI. And to formulate the result, let's look also at what happens for the real numbers. I mean, if you think of it here, we are considering a map from Rm times n, where these are the rank of the matrices, into the symmetric matrices of rank n, so n plus 1 over 2, and we're sending here x into x transpose s x. That's the t. So in a way, we're looking at the fibers of this. So let's look at some sort of density. And we define, in order to do that, let's call it A infinity of ST to be the limit of the volume of, let's consider open sets around T, and let's shrink them to T. So let's consider the volume of Q in the denominator, and in the numerator, the volume of the fiber, the inverse image under this max sigma of mu. And having done that, let's define now the density of ST to just be A bar over A infinity. Moreover, let's do the same thing over any number Q. So let's define, let's say, AQ of ST to be the number of solutions in Z mod Q. And let's now define delta sub Q of ST to be AQ of ST over Q to the, if you think of it, if we are in a finite setting, the fiber there is going to have Q to the n times n minus n times n plus 1 over 2 elements. Anyway, having set up all this notation, let me write finally the result. The result is that the limit as Q goes to infinity of delta Q factorial of ST is actually equal to delta ST. This is not the way it is usually written down. Usually one breaks it down into different primes. But for our purposes, I think that's good enough. Notice that the data here is completely determined by what's happening modulo Q. And the data over there is in a way relating these two values, this one and this one. This is a result of analysis. Essentially, we can compute it. So at the end, we do get some kind of formula for what's happening here. And of course, this formula does imply the previous result of Jacobi and many, many other results. This is in Ziegel's work. This is some kind of central theme. Most of his work is going to be developed around trying to prove this. So all his work on what today we can call modular forms and all these things were motivated in trying to prove this. Okay, so that's the beginning. Let's try now to see what Tamagawa numbers are. Well, Tamagawa numbers have to do with this. And by the way, Tamagawa is a mathematician, Japanese mathematician. And the reason he appears here is that he made a very important observation. There have been a general tendency in number theory to eliminate complex analysis from the picture and to turn it into harmonic analysis. And Tamagawa kind of did one of the last steps of that, because this had begun with Chevrolet and the Veil. And Tamagawa did the following. But before I can say what he did, let me remind you of what the dells are. And in order to do that, I need to ask you to bear in mind that this analogy there is between number fields and Riemann surfaces or algebraic curves. The analogy kind of goes that the analog, let's say, of a number field like the rational numbers would be the field of meromorphic functions on the Riemann surface. And the primes, p and I'm assuming also infinity, are analogous to the points on the Riemann surface. So what are dells? The dells are essentially the following. We have a family of, in the product of the p-adic number, let's say, I got myself in trouble here, such that you should think of the p-adic numbers as being analogs of the meromorphic functions around a point p. So we have this bunch of functions, and we're asking that most of them be regular. In other words, the only poles that are allowed are finitely many. Let's try to take down as the number of APs that do not belong to the p-adic integers, finite. Of course, the nice thing about this is that it's a ring, it's a topological ring, has nice topologies, and it contains Q. And let's now look, I mean, previously Chevalier had kind of used the units in this ring to redo plus field theory. Let's now try to relate these with the previous result, and that's through looking at the group, the special orthogonal group of the matrix S. And if you think of it, this is essentially looking at the X such that XTS X is equal to S. These are algebraic equations, so this kind of makes sense over any ring. So I can look now at the points of this group over the adels, and I can look at the points over the rational numbers. And of course, one is inside the other, and I can take the corresponding homogeneous space. What Tamagawa did is that he realized that if you put a canonical Haar measure on this group, and the way you do that is essentially by putting one on the group applied to the p-adic integers, and then taking the product for all of them, and the basic result you want, the basic identity you want is that if you have this measure, you want that the measure for G of ZP be equal to Q to the minus dimension of G times the number of points of your group over the finite field, in this case Z PZ. So that's the canonical thing you want, and once you set up that Haar measure, what Tamagawa noticed is that that measure, the measure of this homogeneous space, and that's what's called the Tamagawa number. So G A mod GQ, he noticed that that measure being equal to 2 is actually something that implies Siegel's formula in the case S equals T. So that implies Siegel's formula for S equals T, which is the classical Minkowski and so on.
What is small q here?
Where is this? Oh, here or?
Yes.
Yeah, I'm sorry. That should be a P.
Are there real numbers in these adels?
Sorry?
Are there real numbers in these adels?
Yes. I'm assuming that I'm also allowing P to be infinity. Yes.
Is it equivalent? Is this statement equivalent to Siegel's formula?
Yes, but Tamagawa only realized this. Then Undervale jumped into the business. And what Undervale did is to show that actually this not only implies the case S equals T, but implies the whole thing, and they are actually equivalent. This is a paper that appeared in some colloquium on algebraic groups in 1962 or something like that. Yeah. So these are the Tamagawa numbers. And I hope that at least you will share with me the feeling that they are interesting.
Are they always equal to 2?
Sorry?
Are they always 2?
No. In fact, this is a result only for the special orthogonal group, and one of the results of Undervale's involvement in all this is that he started computing them, and he noticed that for G simply connected, he would get 1.
And this he turned into a conjecture. And of course he verified this in many cases. Then the big step here was done by Langlands, who gave a unified proof for Chevalier groups. And over number fields, the last step was done by Cosbit a few years ago, who essentially proved the full result for number fields. For function fields case, in the function field case, that is when you have a curve over a finite field, where you can set up the whole thing. Harder did a calculation in the case of Chevalier group, essentially parallel to the one Langlands did, and in that case it's true. The general case, as far as I know, is still open.
What is true?
That Tamagawa number for simply connected semi-simple group is 1. But as I said, only for the Chevalier groups it's known. And in some other instances, but I think the full case is still open. Okay. So what I'm interested in here actually is the function field case. And the reason I'm interested is this is what happens when you have considered vector bundles over a curve. And in a way, this talk is a continuation of the previous colloquium that I gave some time ago. And I hope I'm going to be able to show you some interesting progress. So let me jump now from here to vector bundle over a curve. And the reason is that in here we have the moduli problem of vector bundles on the curve. And if you put this extra condition of the bundles being stable, you can build up this moduli space, which is actually an algebraic variety. And you may want to find geometric properties of this variety, such as, for instance, the Betti numbers. The first full computation of these Betti numbers was done by Harder in the case of rank 2, and then in the general case he was aided by Narasimhan and some other people. And Harder's idea was to use this Tamagawa number stuff in order to count the number of solutions over a finite field, and then apply the Veil conjectures. In fact, he did the calculation in rank 2 before the Veil conjectures had been proven, so he had to prove them for that particular case. Then Deligne proved the full Veil conjectures, and then with that and the aid of Narasimhan, they were able to do the general case. So the key idea here is that you want to count the number of vector bundles over the finite field, over the curve over the finite field, by using the fact that the Tamagawa number of SLN in the function field case is 1. This has been already proven by under Veil. And in that case, this turns out to be equivalent to the fact that if you sum over the isomorphism classes of vector bundles over the curve over the finite field, so isomorphism classes, and let's say you fix the determinant, so fix determinant, then this sum, this is the analog of that formula there, turns out to be q to the n squared minus 1 times g minus 1 over q minus 1 times the theta function of the curve evaluated at 2 times theta function of the curve evaluated at n. In the same way that the number field has a theta function, curve over a finite field has a theta function. This is nicer because it's a rational function, and this is the function that appears here. The next thing is then to stratify. You stratify all the vector bundles, and you use this formula to count them. And after doing all this, you get some nice formulas. a few years later, Atiyah and Bott sort of started to look at this theory again, and what they found was that they could do the same calculation, but this time, so Atiyah and Bott, they found that they could do the same calculation essentially in parallel, but this time using a covariant cohomology. So what they would consider is all the complex, they would fix the C-infinity vector bundle, they would consider all the complex structures, and they would let the gauge group, which just the complexified gauge group is just the C-infinity automorphisms of the fixed vector bundle, acts on that. And they would do a calculation in parallel, in the sense that they would stratify, and where these guys would be counting points over a finite field, they would be dealing with equivariant cohomology, and they would end up with the same formulas. The key formula here is the fact that when you look at the equivariant cohomology of the whole strata of all complex structures, that's contractible, so you get the classifying space of the gauge group, and this turns out to be 1 plus t to the 2g over 1 minus t squared times p2 times pn, where p of I is just 1 plus t to the 2i minus 1 to the 2g divided by 1 minus t 2i times 1 minus t 2i minus 2. What the Atiyah and Bott noticed is that there was a very nice parallel between the two theories. And this brought them to ask a few questions. One of the questions they asked is, why is the Tamagawa number of SLN 1? They said, this is not very well understood, but analogy with our work would suggest that this must have some cohomological meaning. So this is one of the questions. The other question they asked was that they noticed that when you go from one setting to the other, you're using a transformation that essentially sends q to the t squared and some numbers omega I. Maybe I should say that these numbers appear in the statement, in the expression for the theta function. This turns out to be product 1 minus omega I q to the minus s over 1 minus q to the minus s times 1 minus q to the 1 minus s. So you send these guys to minus t. Well, you will see this is one of the ways of going from here to there, essentially by using the Veil conjectures. But there is another one that works, which is to send q into t to the minus 2 and omega I into minus t to the minus 1. In fact, that one works even better. And they were puzzled. Why should this be? Okay. So let's keep this in mind. And yes.
In this summation here, at bundles over a fixed curve.
Okay, so we have a curve x over a finite field, and we are looking at all vector bundles defined over x and over fq.
Okay, so the summation is over all possible.
It's an infinite number of possibilities.
And over here, what's the summation?
Oh, over here we have no summation. That's the Poincaré series of the classifying space of the gauge group. This is a Poincaré series.
So this is just some kind of large characteristic polynomial.
Well, it's a Poincaré series. That's what it is. I'm sorry I didn't define it. What it means is you look at the cohomology. So pt of bg, sorry, this is sum over all integers of dimension of hi Bg times Ti.
What's confusing is that over here you're counting something, and then over here it's just some kind of identity. Right?
Yes.
And so if you say one corresponds to the other.
Yes, well, I should give more details. Unfortunately, I don't have time for that. But when you set up the two situations, you see that you find a formula that gives you the number of solutions. You should realize that this is not, in a way, the number of solutions. Because what we're going to do is to use this as a measure. See, what we're doing here is we're putting weight 1 over the number of automorphisms. And the point is that for the stable bundles, the number of automorphisms is fixed. So this is always, in that case, q minus 1. So that will allow us to count them. When you do that, you get an expression for the number of stable bundles. And when you look at those expressions and you apply these transformations, you get the expressions that Atiyah and Bott obtain. But here I'm just giving somehow the big expressions that lie at the basis of the whole thing. This is, it's a more complicated process. Unfortunately, I don't have time today to really go into details. Otherwise, I'm not going to be able to do what's coming next. I did do that last time, but this time...
BG is more or less the space of bundles, right? More or less space of bundles, right?
Well, we'll see that in a second. What BG is the maps from X into B of GL and C. I mean, that's what essentially it is, topologically. And that one of the ways of obtaining that is exploiting that result, that statement. But we'll see in a second what that is. Yes, but you're absolutely right. That's what it is analogous to. So let's keep that in mind, and let me now go to the second part, characteristic classes. And you'll see that that's related to this, in the sense that characteristic classes, in my mind, always appear when you have a moduli problem. So, of course, the first instances where characteristic classes appear were where you had, let's say, principal G bundles, and you had an object classifying those principal G bundles. But we could think of other examples. So, principal G bundles. Let's also consider curves. Let's also consider vector bundles over a curve, which is what we were looking at previously. The setting for a moduli problem is that you need, first of all, a notion of movement that's given to you by a notion of a family of, you have this object, and first you want to define or have a notion of continuous movement, or holomorphic movement, or algebraic movement, or whatever. And the idea is that you're going to get to a situation where you will find perhaps an object, let me call it B sub f, to be in touch with the case of G bundles, where that's called BG, that somehow giving a movement parameterized by S becomes equivalent to giving a map from S into this universal object. That's somehow the nature of the game. One could think of these as being some sort of equation where you have an unknown, which is this universal object, and you're given this other stuff. Of course, one has to be careful here, because in some cases you may be able to solve this, but in others you will not be able to. In fact, for instance, one of the problems in the case of vector bundles over a curve is that you cannot solve this in the category of algebraic varieties. But something like that already happens for principal G bundles. If you think of it, if these are the principal G bundles over S, you do not have an equivalence with maps, continuous maps from S into BG. What you have to introduce is a notion of homotopy and look at homotopy classes in here. And then you do get something. This is something that also happens in the cases of curves and vector bundles on a curve. And this is something that Grothendieck, so let me write his name, understood fairly well. And in fact, let me make some publicity for his Cartan seminar of 1960-61, where he kind of formulated this situation in a very global way, and especially he handled the case of curves. And when you look at the problem here, and this is something that Grothendieck observed, you have to somehow look at what you have here. What you have here is usually a category. So you are in what he would call the context of fiber categories. And this throws you immediately into a situation where you have to consider two categories. A normal category would be a one category. A two category would be a situation where the homes between two objects are themselves a category. Think of continuous map and homotopies. That's the best example of a two category. When you consider fiber categories here, you're also thrown into a two category context, and therefore it's very natural to try to solve the moduli problem by going outside your base situation of just algebraic varieties. When you do that, you are thrown into the world of algebraic stacks. And this is something that makes a lot of sense. It's very much like in analysis when you're thrown into the world of distributions. Or in algebra, when you look at the equation x squared plus 1 equals 0 over the real numbers, you're thrown into the world of the complex numbers. Something like that happens here. And perhaps, let me say, for instance, that in the case of curves, there's a common mistake that people make of thinking that this object is the Teichmüller space modulo the mapping class group. That's actually not true. That's not the solution. That's only the, it's like having the real part of a complex number, but you don't have the complex number. It is true that Teichmüller space and the mapping class group give a solution, but in order to do that, you have to consider the quotient as algebraic stacks, not as algebraic varieties. When you do that, then you do give a solution and you have all the nice things. But the variety, the quotient variety, is not a solution. Anyway.
What is it not a solution to?
It's not a solution to this moduli problem. In other words, and this is something that you can find in Grothendieck's Cartan seminar. You know, these will not hold. Okay, but let me not get into that because I still have lots of other things to say. The characteristic classes appear in this context in the sense that characteristic classes become elements of the cohomology ring or any invariant that you may want to compute of this universal object. And the reason is that when you have an object here, you're going to get some map from here to here, and therefore a mapping cohomology. So for instance, the Chern classes will appear because, for instance, so example, the cohomology of the classifying space of GLNC fiber bundles is just, as it is well known, it's a polynomial algebra generated by the Chern classes. Each one in Ci is in H to 2I. And these guys determine the whole ring and therefore determine any map. And these are the Chern classes. These will be interesting to us in a second. That's why I mentioned them. So let's go back to the original situation. And let's try to see what's going on here. Well, what's going on here is that we are dealing really with the algebraic stack, the moduli stack. So let me call vect the moduli vec sub x, the moduli stack of families of vector bundles. In the sense that if you put here vector bundles on S cross the curve, that's what the family of vector bundles parameterized by S is, then that object here in the category of, in the two category of algebraic stacks will provide us with a solution. So we will have a universal family of vector bundles. Let's call it U. This is the universal family. And this universal family now will have, of course, Chern classes and so on. Let me write them, because this is a vector bundle. So we have, right now it could be over any field. I'm not yet there, but I'm going to be there right now. So let's consider the case when X is a curve over a finite field. So now we are back into algebra class. And one of the things that Grothendieck taught us is that in these situations you have a very nice geometry that lies behind the algebra. In the sense that the Galois group, for instance, corresponds to the fundamental group. And lots of objects that appear in arithmetic actually have a geometric counterpart. Like L functions correspond to local systems, and so on. In this case, we are over a finite field. So as it is well known, if we consider the closure of this finite field, there is a automorphism which is called the Frobenius, sending t to the qth power of t. Now, this object here is going to induce for us an endomorphism of the moduli stack. And via that is going to induce an automorphism of the cohomology of the moduli stack. Of course, the first question is, how do we make sense of such a cohomology? Well, the answer is that we have to consider a topos associated to this moduli stack. Toposes are a generalization of an extension of the notion of topological space. Grothendieck introduced them because of arithmetic reasons. There are also geometric reasons for doing that, in the sense that usual situations like foliations do not behave nicely as topological spaces, but give rise to nice toposes. But in arithmetic, it's quite clear that you want to do that. And an example for that is the proof of the Weil conjectures. Without doing this, we could not prove them. Once you do that, what you get is that your cohomology is now not only going to have the structure of a group or of a vector space, but it's going to have this extra structure coming from the action of Frobenius. And this extra structure contains a lot of arithmetic information. So for instance, if this were an algebraic variety, over the finite field, we could be able to deduce the number of points, of rational points over the finite field, out of looking at the trace of Frobenius acting on this algebra. In this case here, we don't have an algebraic variety, so we have to be more careful. But we do have something that is very close to an algebraic variety, and it still makes sense to talk about the rational points over the finite field. It's only that now we have to count things in a careful way. I like to think of algebraic stacks somehow as geometric objects with inner symmetries. So you have to take into consideration that your points now are going to have inner symmetries. And these should come in to whatever formulas you consider. So it seems very reasonable in these situations. So let me say that over here because I don't want to lose those formulas, to define the number of rational points of a stack by counting over, so we look at f of fq. If we're dealing with an algebraic stack, this is going to be a groupoid. So we can look at the path components, at the isomorphism classes in that groupoid. We can sum over those. If this were an algebraic variety, that would just be the points. And now we take 1 over q to the dimension of the stack times the number of automorphisms of x. Of course, the idea for this essentially goes back to Eisenstein, and we've seen how useful that is in the case of quadratic forms.
So all these guys, automorphism groups are finite in your situation, right?
Right. If this has nice finiteness properties, yes. Right. So the analog of what I said before of the number of points being given by the trace, in this case becomes that mq of f is equal to the trace of the cohomology algebra of f over ql, where the trace is with respect to this arithmetic Frobenius. Now that's something that one should prove. Okay? But what I'm going to show you today is that this statement, when you are in this situation here, turns out to be precisely this statement here. So the final answer, in a way, is that Atiyah and Bott and Harder and Narasimhan were really doing the same thing. It's only that one was looking at the group structure in the cohomology. The others were looking at the action of Frobenius on the cohomology. And how will that happen? Well, the way I know of showing that is by computing the cohomology. And the way to compute the cohomology is to use divisors. And this is essentially, this should tie up with the previous lecture. There we kind of exhibit this bridge between the two theories. Let me try to motivate that by looking at another example, which is the example here that we had previously of principal G bundles. We can do the whole thing in that case for an algebraic group. And we also have a classifying stack. And we can also look at a statement of this sort. Let's say we deal with the general linear group. In that case, we have a model for this classifying stack, which is given by looking at the infinite dimensional Grassmannian. So we have this family of Grassmannians, and that has the same cohomology as this classifying space. What's going to happen in our situation is that divisors will provide us with a similar model. So we are able to compute this cohomology essentially by showing that that cohomology coincides with the cohomology of the divisors. And the reason that's good is because we know, let's say, what the Betti numbers of the divisors are. That can be obtained by looking at the torus action on these quad spaces that parameterize the divisors. So we know the postulation. And we have, moreover, a Abel-Jacobi map that goes from the divisors, let me call it divisors, into the stack of vector bundles. And therefore we get a map in cohomology going in the other direction. And it's possible to show that these two provide us with an isomorphism. And once we've done that, it's very easy to show that one can give a very formal description of both cohomology rings by looking at the Chern classes of the universal bundle, taking their Kunet component, and forming the free graded algebra on those objects. There are maps going in this way, because those guys do exist in here. And one can show that these maps are injective, and since we know the postulation, and the postulation coincides with that one, and these two are isomorphic, the whole thing becomes an isomorphism. And I'm not giving details here because I'm going to give you, right in 1 minute or two, a more general statement. So once we are done with that, we can see then that the trace of this cohomology becomes just this part here. And you can see that these 2 to n really correspond to the Chern classes in here. We've lost one because of going to SLN in some way from GLN. There is this other question. In this case, the answer to this comes from the fact that these varieties of divisors that provide this model are actually smooth projective varieties. So they satisfy Poincaré duality. If you think of it, the difference between these two guys is that you obtain this one from this one by sending now t into t to the minus 1, which is essentially what you do when you deal with Poincaré duality. So one can look at what's going on and see that the reason these two give the same result is that these varieties of divisors are smooth projective varieties and satisfy Poincaré duality. Perhaps I should say a word about what these divisors are, and then I'll try to go into a more general setting where the whole thing, I hope, will become even more clear. What are divisors? If you think of Cartier divisors, Cartier divisors are essentially the global sections of, you look at the units of the sheaf of meromorphic functions, let's say, or rational functions, and you mod it up by the units in the structure sheaf of holomorphic functions. And so this is divisors, and effective divisors, effective Cartier divisors are just, you look at the intersection of the units in M with OX, this gives you a semigroup, a monoid, and you mod that out by OX star. Well, the divisors, you can do the same thing here using GLN, So you have GLN of M over GLN of OX. And here you can do GLN of M intersect the matrix n by n matrices with OX coefficients modulo again GLN OX. And this gives you a notion of effective GLN divisor. And one can show that the quad spaces parameterize these guys. It's very similar to the way the symmetric product XD parameterizes the effective D divisors. And those quad spaces have nice properties, and one can compute the Betti numbers and so on.
What kind of spaces?
Quad spaces. I'm referring to my previous lecture. Unfortunately, my problem is that I still have something else to say, which I think is more interesting, and will wrap it all up. I hope. Quotients. It's a technical notion that Grothendieck introduced. I could go into what it is, but I think right now maybe it's better if I don't. It's an analog of the Hilbert scheme, for those of you who know that. Okay, so let's try to put all of this into a bigger context. And the bigger context, of course, is to forget GLN and to look at a general group, algebraic group. And before I do that, to whet your appetite, there is one formula that comes up all the time in these matters. And that formula is due to Steinberg, and it tells us what the number of points of an algebraic group of a finite field is like. It's a very famous formula. And to just give you a taste of things, well, it's possible to show that that formula is precisely this formula here, when you have the classifying stack of the algebraic group of the finite field. If you do this, it comes right, it's clear, you know. You're using characteristic classes in computing the rational points. That's what you're doing. And since I don't have much time, I will not talk about that. But let's go to a more complicated case. We have now a group scheme over X. You can think of this as a family of group schemes. It could be a constant family, like we had before, where you have GLN. And we can consider in the similar way the corresponding moduli problem. And I'm going to ask you, you see, in this formula here, we have this product of values of theta functions. So you may ask, what is this? Well, what this is really is a value of an L function. And the L functions come from constructible sheaves, or this is local systems, essentially. So let me define for you one. And let's just take the primitive part of R star pi low star of QL, where pi is this thing, and add 1 to it. And really, don't be intimidated by this. If this were constant, this would be cohomology. So think of this as cohomology.
Excuse me, X is, what is the dimension? X arbitrary dimension or a curve or what?
X is a curve over FQ. Okay? G is a semi-simple group scheme, let's say. So you should think of this as being cohomology, and I'm jumping by one because what I'm really after is the cohomology of the classifying space. So I have to switch them. So once I have this, now I can form a graded module, which is look at the direct sum for j minus I equal star of h to the 2 minus I of x bar m sub g j. This is the graded module. And I want to take now the universal graded algebra over this graded module. So let me call it H sub G, and that's going to be S, the symmetric algebra of the even part tensor, the alternating algebra of the odd part. And okay, with this notation, it's possible to show that MQ of Fg is precisely the Tamagawa number of G.
What is FG?
Fg would be the moduli space of G principal fiber bundle. So if you think of, you have torsos for G over X, this is something lying over X, and X is lying over FQ, and you can take the direct image. So the direct image of this guy is this. But it's the analog of the vector of the vect that we were dealing with here. So this guy turns out to be just the Tamagawa number of G at the generic point of the curve. That is, for the field of rational functions, times the value of at 0 of the L function corresponding to the dual of this M. And moreover, once you've proven this, you get that Tamagawa number, that this statement here, the trace formula, becomes Tamagawa number equals trace of the cohomology of Fg divided by this value of this L function. In our situation, this value here would just be this. And you see, the nice thing is that this guy here has traced precisely this one. And when G is simply connected, the cohomology turns out to be precisely this one. So in that case, this quotient turns out to be 1. And that becomes then a cohomological statement. I'm going to hopefully talk about these things next semester, if anyone is interested. And there will be more details, and especially details about what algebraic stacks are, and etc., etc., etc. Thank you for your patience, and I apologize for this very chaotic talk. Thank you.
Any questions?
Well, it's true when your stack is, let's say, an algebraic variety, or the linear amount for the stack of finite type. Okay? Your stack is a finite type, then it's proven. Unfortunately, these guys here are not a finite type. So if you look at what this is doing, it's actually proving the trace formula. It's saying that whenever you've shown
The Tamagawa number is 1, then you have the trace formula. So for all Chevrolet groups, let's say, this gives you the trace formula. Kai Varen, which I should have mentioned before, has proven some cases, but he does have some conditions on G that he has. Kai Varen, he's a student of Harder's, and he has proven actually this formula for stacks of finite type. My interest in this somehow is from the other side, in the sense that I think what this shows is that I think morally one should consider this as being the case. And the Tamagawa number calculation should really be a consequence of this. Unfortunately, right now that's not the case. I'm sure it will be in the future. But this has the advantage that it reverses things, and it gives you the formula. This, by the way, another thing that happens when you look at these things and you look at the way the devices enter, then you find a new possibility for computing Tamagawa numbers. Because the classical calculation of line length done by Harder in this function field case uses Eisenstein series. The Eisenstein series, in a way, is looking at the Borel subgroups. But my calculations suggest that if you look at the B devices, where B is a Borel subgroup, you may actually get calculations that give you the Tamagawa number. But that should be for another occasion. But, yeah.
Any other questions?
Thank you.